Now the last thing I want to talk about is free fall. Now free fall refers to any time the only force acting on you is gravity. So for example, if I were to take my keys and drop them, well, there might be a little bit of air resistance acting on them while they fall down, but it's really very slight and can probably be ignored. While I'm holding the keys up, obviously there's another force on them, the force of my hand. Once I let them go, however, there's no other force and they fall in free fall. Even if I were to throw them up, from the time I let go of the keys and they fly into the air until I catch them again, the only force acting on them is gravity. And so while they're in the air, they are in free fall, even during the time they're moving upwards. So that's the key idea. It's free fall anytime there is no force on them other than gravity. And it turns out, experimentally, that any object, whether it's large or small, an elephant or a poodle, if there's no air resistance or air resistance can be ignored, and there are no forces other than gravity, and it's falling near the surface of the Earth, it falls with an acceleration of approximately 9.8 meters per second squared, or 32 feet per second squared. The direction is straight down. That's how we define which direction is down. It's the direction that gravity pulls. And it's constant for all different objects and for all times, so long as we are near the surface of the Earth. Now you may ask, how close is near the surface of the Earth? It is somewhat qualitative, but as long as the distance we fall is much smaller than the radius of the Earth, or much less than about 6,000 kilometers, we're pretty safe. You can go up to a height of probably 10, 20 kilometers before you need to worry much about the variations in gravity. What this means is that because free fall is a constant acceleration situation, we can apply everything we learned about constant acceleration situations in one dimension to free fall. The only thing we have to change is that our acceleration is now g, and we will usually write it as g instead of as a. It's 9.8 meters per second squared. Typically g represents a positive number, so we often put a negative sign on it by hand. And we can use this in the y direction as our one direction, instead of in the x direction as our one direction. And as long as we're dealing with the time when nothing else is touching it, we can use all of our constant acceleration formulas to deal